Hi everyone. Today I featured a song that is Nothing on You. Okay, that I would just borrow this title to illustrate the true meanings of a string. Okay, you just know that in engineering practice, the normal engineering materials we use, like concrete, steel, and even plastics, they are very hard. Okay, normally when we load them, they will deform, but actually the deformations is very small. It's so small that our eye cannot see those deformations. Last time we have defined a string, and we have introduced the unit. So it's unitless. But normally, because the values of the deformation, the strings is very small, so in engineering design, we normally use microstring. Thinking about what is microstring, that is 1 times 10 to negative 6. Okay, how small that is. Okay, so you cannot see that small deformations, small strings. Right, so today we will further understand the string and the shear string. We will give several examples to show how to calculate normal and shear strings. And we will analyze the strings in simple structures. Okay, so last time we talked about how to do stress analysis. Right, then how to do stress analysis. We normally have 3 steps to follow. Right, the first step is free body diagram. Right, the first step is free body diagram. Use that. You can calculate the internal forces. Right, then second step, you calculate A. And third step, just calculate stress. Right, calculate stress. Use internal force over A. Right, those are the 3 steps to do stress analysis. We also define a strain and a normal strain. So what is a strain? Right, since stress is the intensity of internal forces, the strain, simply speaking, is the intensity of deformation. Right. So what is normal strain? We defined normal strain already. Right, please recall the definition. And as shown here, the normal strain is the change in length of element divided by initial length. So deformation is perpendicular to the face of an element. Meaning what? Meaning the direction of the length change delta and the original length is in the same direction. As shown here, this is original length, then the deformation, the change in length will be in the same direction of L. It will become longer or become shorter. It depends on if you are stretching it or compressing it. Right? When you're stretching it, when this element is in tension, then the deformation will be positive and the strain will be positive. Right? If your element is in compression, and the delta will be negative because it will become shorter. Right? So during calculations, you should take care of the signs, positive or negative. This will affect your results. Right? For example, I gave 2 simple examples last time, and we did a in-class assignment. In the in-class assignment, we give a bar that is 1 meter long. Right? After deformation, it becomes 0.999 meter. Right? So what is the length change? Yes, this is a definition to calculate normal strain, and we have given this 2 number. This is original length, and this is the length after deformation. So what is the length change? Length change delta will be calculated as 0.999 minus 1, that is negative 0.001 meter. Right? So this is the change in length. It's a negative number. Right? Negative number because it becomes shorter. Right? Negative. Do not forget the negative sign. Then the original length is 1 meter. So the normal strain will be negative 0.001 over 1. So that is just negative 0.001 strain. If you like a unit, you can use strain. And I saw some students also reported the result as 1000 microstrain. That is also good. Okay, just always keep in mind that you have a sign. So when your element becomes shorter, your normal strain will be negative. Okay, so that is normal strain, and today we will also talk about shear strain. Okay, shear strain, I should put focus here because this is a little confusing. Okay, the shear strain is the change in length of an element divided by the initial length. See that this first sentence is exactly the same as normal strain, but the deformation is parallel to the face of the element. Okay, this is very confusing. Okay, actually the shear strain is a measure of a change in angle between x and y axis. Okay, so the shear strain is an angle, is not a just becomes longer or shorter. It's a change in angle. Okay, so according to this definition, if we say it's a change in length of element divided by initial length, we can use such an equation, and we use gamma. We use gamma to denote the angle of shear strain. It equals delta x over L. If you look at this this figure here, we have the original x here and original y here. They are perpendicular to each other, so the angle between them is 90 degree. But after deformation, after it is loaded by tau xy, the shear force, the shear stress, and it would deform, and you can see that an angle appears here. That this is gamma, right? This measures the change in angle between x and y. Okay, we can also define it using another equation. That is gamma. This based on this definition. It's a change in angle between x and y. We can define the gamma as alpha minus beta, and the alpha is the original angle between x and y, and beta is the angle between x and y after deformation. Okay, so let's illustrate this definition here. So we have this element here, the original element. Okay, you have x-axis here and y-axis here. So after deformation, it becomes this. Okay, the x-axis didn't change, and the y-axis moved to here. Okay, we have y prime. Okay, so here we have the original angle between x and y. Notice here this is the alpha, and after deformation, it's beta here. Okay, so the gamma is here. So as illustrated in this figure, you can see that the gamma equals alpha minus beta. Okay, alpha minus beta. This is very special. This is different from the previous normal deformation, normal strain. Now, when we calculate the length, when we calculate the change in length, we use the size after deformation minus the size before deformation. We got the length change, right? But here, when we calculate the shear strain, we use the angle before deformation minus the angle after deformation. This is different. So you have to remember this. I don't know why, but you have to remember this, since this is just a convention. As shown here, this is a sign convention. This is because of the sign convention. You know, when we calculate the normal strain, when it becomes longer, we say it's positive. When it becomes shorter, we say it's negative, right? But when we calculate the shear strain, a positive shear strain means that the angle between x and y axis becomes smaller. It decreases in deformed object. And the negative shear strain means that the angle between x and y axis increases in deformed objects. Okay, this is illustrated here. So when this angle becomes smaller, okay, we call this is a positive shear strain. And when the angle becomes larger, we say this is a negative shear strain. This is a sign convention here in normal strain. Okay, you have to remember this. About the unit, the shear strain is also a dimensionless, unitless quantity. In engineering, we can express it in radian. Okay, we use radian as a unitless unit for shear strain. But normally these values are very small, so we may use micro strain, micro radian. Okay, micro radian is 10 to negative 6 radian again. Okay, as I said, this is perhaps a little confusing. So let's give you another example, perhaps, to show how can we correctly calculate the shear strain. Okay, let's look at this example. So we have a element shown here. And we have x-axis, y-axis. Right, so this is the element, and the element is subjected to shear. And the tension. Okay, it's subjected to both axial loading and shear loading. Okay, so this thing will be deformed in such a way that it will be stretched along x direction. It will be stretched to here, and it will be rotated because of the shear loading, the shear stress. Okay, we'll have only shear. It will only be rotated. It will not be stretched. But here is in this case, it's loaded by normal and shear, both normal and shear loading. So it will be deformed in this way. So we have the sizes as shown here. This is the original size Lx, and here is the delta x, the lengthening change in x direction because of the normal loading. Okay, and here you have another deformation. What that is, delta x prime, and here is the original length in y direction. This is Ly. Okay, so here let's see how can we calculate the normal strain. Okay, my first question is, what is the normal strain? Epsilon x. So is there a normal strain along y direction? Since we don't have any delta y, so we don't have epsilon y, right? So here's only epsilon x. So how can we calculate epsilon x? Right, the epsilon x will be the deformation length, change in length along x direction over Lx, right? So this is a normal strain, epsilon x along x direction. Is this positive or negative? Positive or negative? And since it becomes longer, right, so this is a positive normal strain. Then how about shear strain? How about shear strain? As we mentioned previously, we have two methods. We have two methods to calculate the shear strain. So the first method is direct method. Let's call it a direct method. Use the first equation for definition. The gamma equals what? Equals delta x prime. It's shown here. This is this value over Lx or Ly. Right. So this is Ly this time. Right. So these two values, should be in perpendicular to each other, not in the same direction. Right. So we also have a indirect method. That is using geometry, right? As we defined in the previous slides, the gamma equals alpha minus beta, and the alpha is the alpha is what? Alpha is the angle between x and y before deformation. And then how about beta? Beta is just after deformation, right? So where is this alpha? This gamma? This gamma is just here, right? This is the gamma. Right, since our alpha is here, this is alpha. Alpha equals what? It equals 90 degree or pi over 2, right? And after deformation, this is the beta, right? So now let's see what happened here. These two should be equal to each other, right? You can see that the gamma should be an angle, right? Since the gamma measures the change in the angle between x and y axis. The gamma is an angle. Is this an angle? Delta x prime over Ly. Is this an angle? Okay, this looks like it's not an angle. But how can we use delta x prime over Ly to denote the angle alpha minus beta? Okay. So what is this? What does this mean? If you look at this equation, gamma equals delta x prime over Ly. So what does this mean in geometry? So this is actually sine. This is sine alpha. Sine gamma, right? So this equals. No, this should be tangent gamma, right? This is tangent gamma. So in what conditions tangent gamma equals gamma? Right? If we say this gamma here, it equals gamma, but it actually equals tangent gamma. So it means that in our assumptions, gamma equals tangent gamma. So under what conditions gamma equals tangent gamma? So only when this gamma is very small. It's a very, very small angle. Okay. So this is our one of our very important assumptions in mechanics materials, small angle, small deformation assumption. Okay, so this is our one of our very important basic assumptions. This is a basic assumption in mechanics of materials. It's called small deformation. Small deformation assumption. Okay, we only consider this only when this deformation is very small. We can use this equation to calculate gamma, and only when this deformation is small, where this delta x prime over Ly equals alpha minus beta. Okay, this is a precondition of this first equation, this direct equation to calculate shear strain. Okay, in this example, you can see that we have only one gamma. Right? You have only one gamma. This is alpha minus beta. You get the deformation. Right? You get the change in the angle. And in some other cases, you may have two angles, like you have the delta in both directions. Let's see here. This is another example. So originally we have this element, and this is your x-axis, and this is your y-axis. So after deformation, we get this shape. Okay, after deformation we get this shape. So here is the x prime, here is the y prime. Okay, this is our beta, and here is your alpha, right? So if we want to calculate the gamma, we should use alpha minus beta, right? So what is alpha minus beta? So we have two components. The first component is here, the second component is here, right? So let's call them gamma 1 and gamma 2. Okay, if we know these deformations, this deformations here is delta 1 here. Delta 1 equals 1 over 16 inch. And we know this delta 2 here is 1/8 inch. And we also know that the original length here is 25 inch. Original length here is 42 inch. Okay, those are the conditions. So the gamma equals alpha minus beta equals what? Gamma 1 plus gamma 2. Right, so what is gamma 1? How can we calculate gamma 1? So gamma 1 here should be delta 1 over 25 or 42. Should be over 25. Okay. These two values should be perpendicular to each other, not in the same direction. Okay. Then plus delta 2 over which value? 42. Okay. So you get 0.0025 plus 0.003 or 0.0055 radian. Okay, So this is how we calculate the shear strength in more complicated case. And we also mentioned that this equation, the first equation, the direct equation to calculate gamma, is only valid when the angle is very small. Then how small is small? How small is small? Now here I compared these two curves, right? These two curves. The first one is the tangent gamma, okay? Tangent gamma, and this green color is sine gamma, and this red curve is equal line. So you can see that you can assume gamma equals tangent gamma equals sine gamma when this gamma is very small. So how small is small? As shown here, when it is smaller than 0.3 radian, perhaps just when gamma is smaller than 0.3 radian. Okay, so we can assume that the gamma equals tangent gamma equals sine gamma. Okay, so normally in our mechanics of materials, we have much smaller. Our gamma is always much smaller than 0.1 radian. So this is always valid, normally valid. Okay, you will see in some of our examples, when this gamma is not that small, you will not be able to. You cannot use this equation. Okay, you will use geometry to solve the shear strength.